welcome everyone to this standardization training session number 4, organized from the Value 3S with the help of David and lots of folks that were involved here. We're going to talk today about V&V methods towards certification of aerospace. I wouldn't specify it more on the control concepts, generic for aerospace prototypes. The part of this training will be split into two main parts. One will be more of the dive into the current regulations that we have to face from the aerospace domain. So you will hear lots of acronyms of system safety and down to hardware assurance, software assurance, and then what types of regulations we have using existing model-based design approaches or formal methods approaches in order to verify our designs. So particularly the focus will be on the DO-178C and its supplement, the DO-333, with respect to formal methods. And the presentation will be given from myself and George, usually as UTRCI, but now we are part of Collins Aerospace. So two parts for these presentations. One more of the high level and a dive into the series of documentations that we have on the aerospace side, and the second one will be a much more practical approach to how are we trying as a company to comply with these standards. You will see that, and as part of the Value 3S project, there is a lot of efforts on the requirement side. So what we so-called requirements formalization, it is a process that we have to start from the beginning in order to ensure a series of, let's say, advantages that we can have, whether we try to have correct requirements, not conflicting with each other, but more importantly, mechanize those requirements in order to generate monitors. Maybe some of you might heard on the formal method side, generate, if we can, LTL, linear temporal logic specifications in order to use them from the formal methods perspective. The reason to do this is the word that we hear a lot of times in this presentation, traceability. So we would like to pretty much be sure that the requirements along with the design cycle of an aerospace prototype, we don't want to change, but more importantly, we would like at each step to show that the requirement is being met in all of our models, in all of our prototypes, whether we're talking about models or source code and so on. Okay, so many of you have heard about these DOs documents. So I just took a snapshot of, let's say, the series of requirements that we have to go as let's say, a verification team when we try to build software from the avionics perspective, from the aerospace side. So there is a high, I would say there are two high-level requirements. Obviously, we're talking about safety critical systems here. So there is the top safety assessment process requirements, the ARP 4761, that obviously we have to comply with some safety regulations, but this requirement is going, let's say, side by side with the ARP 4754 for the whole aircraft system development process. Now, when I'm talking about these documents, consider them that the engineers today they are writing high-level system requirements from the aircraft perspective. Usually, big airframers, they are coming into aerospace service providers like ourselves, and they are pushing to us some of these high-level system requirements that our systems or subsystems needs to comply with. So all of these documents, they are taken into consideration when we would like to go and show that a specific, let's say, system or subsystem on the aircraft perspective meets safety requirements, meets a specific, let's say, set of functional requirements. But not all of the requirements, you understand, they don't have the same priority. So on our side, we have a DAL A until DAL E criticality for those requirements, starting from the most serious of the requirement that is DAL A. You can consider that the control that we are placing on the FADEC, which is the device, the fuel authority digital control device that is controlling the engine of the aircraft, it has to pass a DAL A certification, and then we go down to DAL B, C, D, and D, where let's say the DOs, they don't have much of let's say application to those. So how do we do all this? How do we gather all of these different documentations, all of these guidelines, and how do we try to develop workflows and how to define, let's say, I would not go and push it like more agile methods, but more correctness methods when we are trying to develop prototypes of the aircraft. You have to understand that at each, let's say, prototype that we come into, we have to sit down with our customers, with our engineers, and try to see whether we've met all of the requirements, where there are associated test cases, whether we are talking about high-level requirements, the HLR, or low-level requirements, the LLR, for the specific, let's say, software architecture. Now, if the prototype that we are building, it's much more of a high priority of a DAL A or a DAL B, let's say, criticality, we have to push for testing, we have to push for software quality analysis methods, even down to the object code that we are producing from our source code. So there is a series of steps, somewhat does feel like the waterfall, let's say, the waterfall model, starting from requirements, high-level requirements, mapping those requirements to our architecture, mapping this architecture to low-level requirements, and try also to connect those with the source code and the object code that we are getting. Now, for each of these steps, there is a specific plan, software quality assurance plan that we have to define in order to pass all of these steps. And as you can see, all of these obviously we will mix a little bit around within what is testing, what is verification, and when should we use one another. Obviously, whenever we can use formal methods, we do use it, and we save ourselves of a tremendous amount of time and cost with respect to testing, with respect to, let's say, other much more mature, I would say, software quality assurance or software validation, let's say, operations, with respect to the coverage that we need to hit. And the coverage is another part of the story which has to be shown in, let's say, for example, an MCDC coverage for DAL A requirements, but it could be relaxed later on for less, let's say, critical requirements. Okay, so a series of documents used by airframers, for example, at the aircraft level, like the ARP 754, flowing down to us system level requirements about the whole aircraft. You could see inside there that we have requirements from a safety perspective. You could see that we might have requirements from a system integration perspective. All of these high-level system requirements, at some point, we will flow down to us low-level requirements. For example, integration testing, when we would like two different subsystems inside the aircraft to communicate with each other, it has to pass a series of, let's say, for example, message integrity when you are using the AFDX, for example, protocol inside the aircraft. You have to be sure that the message is being sent from one entity to one device to the other has to pretty much comply with, let's say, with a quality assurance of the message being delivered by the rest of the devices. At the same time, there are two major blocks here, and we're going to focus on the DO-178C, particularly for the software side. So we have the hardware and the software. These two, I would say, these two documents, they are quite, they follow a similar pattern. Exactly the same requirements and the same processes that we would like to validate and verify if we can from the hardware. In the hardware development life cycle, we would like to have it as well on the software side. But as many of you might know, hardware is easy, and maybe I would rephrase it the other way around. We tend to build software that is much more complicated or of a high complexity. So software is the biggest trouble for us, because on the software side, you might call off libraries, you might have inter or inter-procedural calls with other, let's say, software processes. There is a level of complexity on the software side that we try to attach to mature testing or even formal methods of verification where we are able to do it. So turning down to the DO-178C, obviously, as I mentioned earlier, there is a series of software lifecycle plans that we have to do when we develop our software, whether this is starting from the initial requirements, how to map these requirements to the architecture, how to maintain those requirements down to the model side, so what type of models we are building and which model is for which requirement, and then how this can lead to the software coding process and later on to the overall integration. So ARP 4754A, they do discuss about how we're going to capture our requirements, how we're going to validate them in the complete, let's say, process. There are several, let's say, amendments, or I might say not amendments. There are several, let's say, key points that we would like to raise here. Like, for example, the ARP 4754 recommends an analysis, modeling, and simulation, obviously the testing for all of these requirements, that it has to be used, let's say, from the system that we need to validate. So, if you're asked, do we have aircraft models? Yes, but not to the extent. Don't imagine that there is a complete, full-fledged, detailed aircraft model that we are able to do this requirements testing. We would like to move into that direction, and there is a lot of efforts right now moving complete aircraft virtually or maybe into the cloud and try to have a much more, let's say, collaborative methods to run all of these simulation and testing. But for our side, when we are developing, for example, an engine aircraft controller, there are parts of the aircraft, obviously, that they are abstracted away, but there are parts of the aircraft that we would like to excite in order to see how our prototype will react. So all of these ARP 4754, they bring us down to obviously the devices, which consist of software and hardware. So the DO-178C for software, DO-256 for hardware, and particularly for the software side, we have to look into the supplements that the FAA and the standardization authorities have produced. So there are three main supplements here to remember. There is the DO-331, which is based for the model-based design. So what type of models we can use to validate our software or hardware processes. There is the DO-330, which is what types of tools we can use to do this verification and validation. There is the 333, which is whether we have methods, mathematical applied formal methods that can create certification credit for us to use later on into the analysis. So a little bit more diving in. So elements of the ARP 4754. We have defined the system design work process, which pretty much we consider it like we have a requirements management plan, and we try to flow down some of the safety requirements down to the best, at least of our understanding, to the series of low-level requirements, or maybe I would say to the block of the architecture that controls a series of low-level requirements that connects to this item. At the same time, apart from the system design work process, we have process and product control. So imagine that the different, let's say, elements that they are part of your system, they have a different configuration. And whenever something is being updated, whenever something is being, let's say, changed, there is another difficult task to be controlled, which is the configuration of the whole system. So different configurations could lead to, obviously, to different, let's say, systems behavior. So we need also to control what is the current configuration from a system perspective, and then flow down again whether this will offer us some design assurance, whether this will be acceptable from a certification, let's say, perspective. And all of this towards ensuring the safe product, the safe aircraft operations under all conditions. So how these requirements are being controlled, let me say, as said, we do have currently, let's say, there are lots of mature methods and processes to try to translate these requirements and the assumptions that these underlying requirements have into mechanized artifacts that we could use later on, as you're going to see from George's presentation, that we could use them for a series of tests, whether this is for testing, whether this is for verification, or whether this is for identifying conflicts between the requirements themselves. Don't forget that there is a series of different multidisciplinary engineers that they contribute to a different set of requirements of the same product. And when I say different, meaning imagine a mechanical engineer writing a requirement, imagine a software engineer writing a requirement for the same system. They have a complete different terminology, they have a complete different, let's say, notion of the system. And we do find that there are usually in large system, let's say, validation efforts, there are conflicting requirements with each other that could delay both our system prototyping and verification, but more importantly, delay our certification. So one part of these managed requirements, you will see them, it's much more on the top-down perspective, and this is what we try to be interesting too. So how to ensure traceability of the requirements from a high-level system perspective down to our models, even down to the code, even down to the object code when it comes to delay certification. But there is also the design-based analysis, which is pretty much consists of reviews from our engineers, and usually it's a bottom-up, let's say, approach. So, as I've mentioned, there is the DO-178C, the software development process. It does follow a little bit the waterfall, let's say, model of the design cycle development. We start with the system level requirements. Most of them, as I said, coming from our customers. We are decomposed, or we try to clearly define which are high level requirements. In our design process, we split those to what is the software architecture that will pretty much ensure, I would say, conformance or correctness to some of our, let's say, baseline safety cases. But more importantly, how do we map some of the blocks of these architectures to our lower level requirements, the actual, let's say, functional code that it will meet our criteria. And then moving down to the source code, we will have to use during the operation of the source code the let's say the latest or the more mature model-based approaches that we can use in order to automatically bypass some of the coding that in old times the human hand was introducing, right? So we have to be able to see what type of automatic code generation approaches we could use, whether these tools that they are generating their code, they are qualified, which is the DO-333 tool qualification, particularly from a software perspective. And when I say qualification is, we have to see if the tools is, for example, generating counterexamples, if it is logging, and a series of tests that each tool needs to pass in order to be DO-330 qualified. But then moving down to, okay, we've discussed about requirements, DORS documents, if you may say. Lots of people, they are using requirements management tools, and try to connect those documents, try to map those requirements from the high level system perspective down to the low level. How do we use tools to automate the process? Keep in mind, this is an extremely cost process. We would like to reduce our costs. I could give some examples from a motor drive system department in the UK. A certification of, let's say, controller for a motor drive for the actuation could cost easily 2 or 3 million per year. And the reason to do this, the reason behind this is that there are different teams coming together to try to see whether each requirement has a test case, associated test case, and whether this test case is proving to us that our requirement is being met. So from a software perspective and the verification objectives that we would like to hit, there is a series of objectives that are being mentioned inside the DO-178C, and those objectives spans from a series, I would say, of default objectives. So compliance, the accuracy that we would like pretty much to get, consistency and verifiability, conformance to specific rules, more importantly from the rules coming from the ERP 4754. Traceability, this is the biggest one that we would like to focus, especially when we would like to move to the software certification at system level, where lots of people, they are involved in different parts of development of the system. And the algorithmic aspect, of course, we will try to see the accuracy of the algorithms and whether or not there is a compatibility issue with respect to the underlying hardware that will pretty much port the software and execute it, right? And there are a series of activities that we already done in the past, let's say 40, 50 years, as let's say a UTC or an RTX, a Raytheon technology perspective. So there are methods, documented workflows and methods to review our outputs from a system perspective. There is a lot of, I would say, there is a lot of experience with respect to the analysis and the tests that we run, tests that could start from a laboratory perspective, but also move to the to test flight scenarios or test rigs. For example, if you're building a motor drive, there is a specific test plan for the completing for the motor drives that you're going to place into the aircraft. So we have a test rig in the laboratory. There is the biggest test rig in the right wing, for example, of the aircraft, and then we move to flight testing and so on. So how do we accelerate this? How do we try to see where formal methods could help us? Or many of you might say, okay, how can values contribute to this? So objectives taken from the software, let's say, from the DO-178C, we try to see which types of objectives we need to comply to, even starting from the system level perspective and going down to even to the production of the executable object code, what types of tests we would like to do, and how we can accelerate things. So this is taken from the from the DO-178C, and we try to highlight how this, let's say, we try to highlight where our testing can pretty much help us with respect to compliance, with respect to meeting the requirements from system level and lower level. And this is where the DO-333 and the formal methods opportunity, or I would say the formal methods and the model-based design opportunity comes. Because whenever we try to use formal methods, we have to pretty much specify um, a model that we would like to execute the state space exploration against one requirements. Don't forget, we have to take the assumption that our model is correct. We have to take also, we pass from a phase that our assumptions, they are correct. So starting from traceability, compliance with the system with requirements, we do develop a specification model that leads pretty much to our overall design model from a software perspective. And those models will consist pretty much from the software architecture and the low-level requirements. Whenever we can automatically code generate with certified code generation utilities, then would be acceptable. At the same time, particularly for the low-level requirements, there is the point that we would like to see whether we do we whether we are conforming to those requirements or not. So moving down, so there are, as I said, we discussed about the ARP 4754 and how recommendation of the usage of these models are helping us to capture the requirements. And we do focus into the models that we are introducing from a software lifecycle perspective, but what type of, where is the exact point to use formal methods to help us verify and extract certification credit, right? So as part of our process, we try to tie the DO-178C and the DO-333 for the formal methods with an acceptable model-based design process, so the DO-331. This is why you see it whenever we try to develop a model. This model has to be part also of a model-based design process. The reason behind it is that we are moving towards an aircraft that is much more integrated. Maybe some of you have heard of more electrified, more connected aircraft. The reason behind it is that models, as you might know, they are reusable to a certain extent. And at the same time, whether if someone is building, let me say, a cyber physical systems model for the complete aircraft, we would like to be able to use this as the top level system model for the ARP 4754, and then connect this cyber physical model down to model artifacts that we could use for applying formal methods. So there is a part that we would like to map the DO-178C objectives down to the model-based design artifacts that we have. And the reason behind this is whenever we want to try new custom or new, let's say, requirements that were flowing down to us from Boeing or Airbus or from our customers, then there is a first to be tried inside these models. And there are specific, let's say, model usage examples that we have identified where high-level system requirements guidance from the ARP 4754 applies to. And there are other examples that they are split between the system level and the software side, where we try to see how can we map high level or low level requirements to the model that we are developing. Okay. So, and let me check a little bit my time because I don't want to, I want also to leave some time for George. So, as said, objectives of the DO-178C. There are cases that we are using, well, I would say the majority of the cases that we're using, it is based on review and analysis. And I know that you see the repetition of this word. We do include inside this analysis testing as our primarily, let's say, validation and verification method. But before that, we would like to see on the software side, in the architecture software side, what type of algorithmic aspects we could verify, where on these cases we can include formal methods. And to do this, there is the main questions that are imposed to us from our engineers is, okay, and you have to understand that these engineers, they do their work pretty good, and even the past 20 or 30 years. So they know about formal methods. They, at some point, they would trust formal methods with respect to getting some guarantees out of automatically, let's say, proving that their models are correct. There is a series of questions that are coming back to us. So how do you document assumptions? How are you sure that your assumption is strong or weak? And how do you justify that it is correct? And this is the part that formal methods is helping us. We try to see whether our sub-models at a specific level, our assumptions are strong, and definitely they are correct. Now, if we pass this level, then this correctness of our models during, let's say, the usage of formal methods, we are trying to see whether the results that we are getting from the verification, let's say, perspective, they are correct, or they have any types of discrepancies. But all of these results obviously have to come from a property to be verified against our models. So this is mapping point from the system level requirements down to the so-called monitors that we use, LTL or temporal logic specification that we are using in the formal method side, and later on as monitors when we would like to use this as let's say test generation, let's say. I think this is one of the latest slides, but what I wanted to highlight is compliance with system level hardware, software requirements, and whenever we can show verification or certification credit using the formal methods is a tremendous, let me say, acceleration and benefit for the industry in general. So whenever we can cut test generation, whenever we can cut costs of an engineer trying to benchmark or test his prototypes using formal methods, it does save us both time, engineering cost, and lots of money with respect to the certification authorities. So we try to push this whenever we can, especially in the software hardware specification. Also, on this, as I mentioned earlier, we might have a much more complex system where there is the need to have a software-to-software integration case. Again, there are several tests that we try to pass, whether these tests are coming from a disaster scenario of abnormal inputs inside our, let's say, entries to the software. Whenever we can use formal verification, of course, we try to do it for strengthening, I would say, the system level assumptions that we have taken that we are mapping down to our software or our hardware side. Let me give it to George. I know it was a lot of talking, and hopefully let's save some time. So I said you're going to see a real case, a tool that we have developed in order to formalize our requirements. Some of those requirements, you might say, span from documents or even images of documents. So there is a complexity of maintaining those requirements, verifying that they are correct, and later on, how to use these requirements, mechanize them. I use this word a lot. Mechanize those requirements to be used as temporal specifications in our selected formal methods tool, or monitors to generate tests. And at the same time, what are the tools that we are developing also as part of values that we could extract certification credits for some advanced, let's say, controls concepts, that software control concepts that we try to build for let me give it to George. George, are you there? Can you hear me?
Yep, thanks, Telios. Let
Do
me
you
share
want
my
me to?
screen.
You can share
Yeah.
your screen. Okay. Okay. Let me stop sharing.
Let me know when you can see my screen.
Yeah, we can
Yes.
already see your screen.
Okay, perfect. All right, so traditionally in model-based system engineering, requirements are maintained in natural language. They may contain ambiguities which, if identified too late, in the
Uh,
worst case, you might
George,
receive.
are
Yes.
you sharing your slides just because we see the Microsoft Teams? So
Yeah,
Oh, really?
yeah,
yes.
No. Let's see. I shared the.
now I can see myself.
No, this is. So you just see the.
The Teams environment, yes.
Yes, the Teams
Oh,
environment.
this is. Can I just put the entire screen? On the entire screen. Do you see
Okay.
the slide?
Yes.
Now it's
Okay,
good.
perfect.
Yep.
All right. So I was saying that requirements are maintained typically in natural language, and they may contain ambiguities that, if they are identified too late, you might even have to throw your design and start over. Tests and monitors are created manually, which is time consuming and error prone. And in general, having requirements in this kind of unstructured format prevents many analysis and tool support opportunities. All of this can be prevented if requirements are written in a formal language, but this is not done typically, mainly because this process requires too much effort for a large existing body of requirements. Now, we wanted to address these issues, these problems, and the solution we proposed and developed in order to achieve this is this requirements formalization workflow that you see here. Now, the core idea behind this is the creation and maintenance of a growing pattern library and a grammar based on automatic processing of a large amount of legacy requirements. This leads to huge acceleration in formalization for both legacy and new requirements. How is that? Uh, in the case of legacy requirements, instead of formalizing, let's say, 1,000 requirements, you only have to formalize, say, 50 patterns, and the requirements that follow the same pattern are automatically formalized based on that. And in the case of new requirements, uh, we have also developed an editor with syntax highlighting and auto-completion based on the grammar derived by the patterns. Of course, it may be the case that for some new requirements, we don't yet have a corresponding pattern, but in these cases, we simply go through the same process of pattern extraction and enrich our pattern library. And now once we have formalized requirements, we can do all sorts of things. We can perform consistency checking, which prevents early errors to propagate through the design phase undetected. We can also automatically generate monitors. Monitors are basically requirement-based models that can be coupled with the system model and can be used for runtime monitoring, for test case generation, for as well as for formal verification of the design. All right. So in its current state, the workflow is implemented in a user-friendly interface that allows interacting with all parts of the process, from importing natural language requirements and pattern identification all the way to requirements formalization and model generation and consistency checking. Now, for pattern identification, we first use some off-the-shelf natural language processing tools, as well as our own rule-based heuristics on top of that, in order to pre-process the text, for example, by trying to identify and abstract away domain entities, mathematical expressions, and so on. And then we use a hierarchical clustering algorithm to group the abstracted requirements into clusters. And now abstract requirements, let's say representatives of the corresponding cluster, are essentially the patterns that we're looking for. It's like this is an example. You can see here, if mathematical expression, then signal name shall be set to mathematical expression within time duration. Now the formalization process that follows is manual, but we make sure to make it as painless as possible. So clustering already helps a lot, as instead of formalizing 1,000 requirements, when we have to formalize 50 patterns, for example. And then another way we help this is we offer some high-level specification languages. So we support several of those, uh, namely PSL, this stands for Property Specification Language, the SPEAR, Domain Specific Language, and the SALT, Domain Specific Language. Now, this variety, let's say, this was done for mainly for two reasons: ease of use and tool interoperability. All these languages are based on LTL, linear temporal logic, which is, I would say, one of the most widespread formalisms for property specification. But they are, in a sense, more high level than LTL. And imagine that formalizing requirements in these high level languages versus doing it in LTL is like programming in Python or MATLAB versus programming in assembly. So it's much easier for the industrial engineer. Okay, so once we have the formalized requirements, as I mentioned, we can perform consistency checking, which in our case works across specification languages. And if requirements turn out to be inconsistent, it also provides a minimal set of requirements that are responsible for the problem. Formalized requirements can also be used for model generation. And here, actually, we have our own state-of-the-art algorithm, which I will describe in a little bit more detail in the following. And I should also mention here that we have already applied this, the developed workflow, to some use cases from our business units with very promising results. And if you want to learn more about this, we also have a short tool paper that describes the workflow in a little bit more detail than I could fit in a couple of slides. Uh, all right, so as I mentioned, we use our own state-of-the-art algorithm for model generation. In our case, a formalized requirement typically consists of the so-called temporal part, uh, what you see in red here, and then we have some embedded mathematical expressions that act as atomic propositions. They are basically the green and the blue parts. Uh, so in our workflow, the mathematical expressions are translated into Simulink block trees, and the temporal part is translated into a finite state machine represented as a state flow chart. And this last translation of the temporal part is actually where we use our own approach, uh, which I'll briefly outline here. So first some motivation. Why do we need to get another translation algorithm from LTL to automata? Well, the thing is that typical translation approaches uh, usually construct an automaton based on syntactic manipulation of the LTL formula, and they build an automaton that there's an intermediate, let's say, automaton that they subsequently determinize and minimize. And one major drawback of those approaches is that this intermediate automaton can be considerably large and even exponentially larger than the final result, what we actually need. And this can lead to uh, needless, waste of resources. Uh, the approach that we developed does not have this limitation. Our algorithm returns a minimal automaton with respect to number of states, and it also guarantees that all intermediate results have strictly fewer states than the final result. Now, our translation approach is based on Anglin's L-star algorithm for active automata learning. In this setting, a learner tries to identify an automaton by submitting queries to a teacher. Uh, and then basically this happens. This is an overview of the algorithm. Initially, through some membership queries, it fills up a data structure called the observation table. Once it has enough information, it builds a hypothesis automaton, submits an equivalence query. In our case, this is implemented using a model checker. And then depending on what the model checker says, the algorithm can either stop or it can generate more queries based on the counterexample given by the model checker. And this process repeats until we eventually have the correct automaton. Now, very briefly, some results here. So these are some example properties that show how we perform compared to other translation strategies. We have these two counter property families. These are properties parameterized by the number of next operators, the number of x's you see in the text. Uh, so you can see that the running time of the other tools explodes in at least one property while ours remains low in both. Let me see how much. Okay, I have 7 minutes. Okay. And in case you're interested in learning more about this, this is the publication you can look at. All right, so for the final topic on my side. So the other thing I wanted to talk about is simulation-based verification. So this is, what I'll show you here is essentially an early version of the silver tool we've been developing. The main idea behind this is to replace regular computations on floating point numbers with set-based computations on intervals. Now, there are plenty of ways to represent intervals with various trade-offs between computation accuracy and efficiency. The basic idea is interval arithmetic, where each interval is represented by two numbers, two endpoints. Another way, which is what we use here, is affine arithmetic. Here, each interval is represented by an affine form using a constant term and a linear combination of symbolic noise variables that you can see here, ranging from -1 to 1. Now, this representation allows us to keep track of first-order dependencies between computed quantities, which leads to typically high accuracy results even for long-chain computations. And affine operations like addition and subtraction are exact in affine arithmetic. However, non-affine operations like multiplication are typically approximated by an affine operation plus an error term that conservatively bounds the result by introducing a new symbolic knowledge variable. And this was one of the initial problems we were trying to solve using this affine arithmetic framework, this simulation-based verification framework. So there's this equation called the matrix Riccati equation. This is for some particular control problems, this needs to be solved online, and in many cases several times during operation of the system. And one way to solve this is this iterative algorithm described here, this evolution of different equations. Uh, but the thing here is, while there are theorems talking about asymptotic convergence of this algorithm, there is nothing known about the exact number of steps needed for convergence given a specific input. And this is what we wanted to do. We wanted to go a step further here. We wanted to get a tight bound for the number of steps required for convergence given a specific range of input matrices. Now, this is useful because having such a concrete bound during the design phase, it can allow you to better optimize, for example, your control approach, as you may be able to even decide that you can reliably get the same results with cheaper hardware, let's say. And here are some examples of the results we are getting with this approach. Basically, we apply the affine arithmetic framework, the simulation-based verification framework on two algorithms. On the left, we have this iterative algorithm that computes the actual solution to the Riccati equation. And on the right, we have a formula, a more conservative formula that gives us a bound for the number of steps. And again, if you're interested in learning more about this, you can take a look at the publications here. And I think I'm done. That will be all from me as well.